Alright, we're going to get started with Lesson 2, Part 2, the equilibrium expression. Now, in Part 1 of this lesson, we learned about the equilibrium expression, we learned about Kc and how to solve for Kc with the equilibrium expression. We understood or learned about how we can use Kc to predict the equilibrium expression, and we also learned a valuable method in solving for Kc using the ICE method. Alright, so those are some principles or things in part 1 of lesson 2. Now, we're going to skip to the end in your notes of lesson 2, and we're going to look at what is called the reactant quotient, Q. Okay, now this is an important idea to be able to understand what we mean by Q. Okay, so let's say that we are in the middle of our reaction and we freeze it in time. Okay, so the reaction is going on and we freeze it. We stop the reaction somehow in time. And what we want to do during that freezing time is we want to take the concentrations of the reactants and products at that time, and we want to determine if we've reached equilibrium or not. And if we haven't reached equilibrium, which direction is the reaction proceeding in? Is it proceeding more towards the products, or is it proceeding more towards the reactions? So basically all we're doing is pretending that we're stopping the reaction at some time. Alright? So this brings in the reactant quotient, okay? Which means Q is a measure of the relative amounts of reactants and products represented in a reaction at a particular time. So its value is to determine, really, from substituting the concentrations of the reaction components and all measured at the same time into the equilibrium expression. That's simply, all this is saying is we're basically going to stop the reaction, like I said, at some time. And we're going to take the current concentrations of both reactants and products, and we're going to throw it into the equilibrium expression, and we're going to solve for Q. Alright? It's the same way in which we solve for Kc. No difference. It's just that we don't know if we've actually hit equilibrium or not. Alright? And so Q is going to help us to understand if an equilibrium has been established or not. So, comparing the value of the reactant quotient, Q, at a specific time in a reaction with the value of Kc for that reaction enables us to predict then the direction that the reaction is going. Alright? So, what you have to understand is being able to take the value of Q, the reaction quotient, and compare it to the value of Kc for the reaction. And that comparison should lead you to one of three things. One is that the reaction is still going to the right, or the reaction is going to the left, or the reaction is established equilibrium. Okay? Now, how do we know this? Well, if the value of Q is less than the value of Kc, then the reaction proceeds to the right, and we're still forming lots of product. Okay, so that means that the forward reaction at this current time is more favorable than the reverse, just at this current time, the snapshot of the reaction that we're currently looking at. All right. However, if the Q is greater than Kc, then the reaction needs to proceed to the left, and it's reactant favored. In other words, the reactants, or the reverse reaction, is going at a faster rate than the forward, and we're producing more reactant at this particular time in this course of the reaction. But if we find that Q is equal to Kc, then the reaction has already reached equilibrium, and so there's no net reaction occurring. In other words, the forward and reverse reaction are occurring at exactly the same rate, and neither direction is favoring the other direction, okay, at this particular point. So again, Q is just a way of taking a snapshot during the course of the reaction at some time and just finding out which way the reaction is going. Does the forward reaction go faster, or does the reverse reaction going faster at this particular time? Or maybe both reactions are occurring at the same rate, and that's when Q is equal to Kc. All right, so let's look at specific problems and see if we can help us to figure this out, okay? So what we have is a reaction here. It's in your notes, and it says the equilibrium constant for this reaction at 500 Kelvin is 1.7 times 10 to the second. Okay, so obviously, if you look at this, the Kc value, erase that. The Kc value for this reaction is greater than 1. All right, so ultimately, the reaction should be product favored. Okay, ultimately, when the reaction is hit equilibrium, there's going to be more product than there is reactant. Okay, but what we're going to do is we're going to take a snapshot of the reaction. What that means is we're going to determine whether the reaction mixture is at equilibrium when the concentrations are as follows. Okay, so at some point in the reaction, we look at these concentrations that are happening at this specific time, and we're going to solve for Q. And then the value of Q is going to let us know if we've hit equilibrium or not. So let's do that, okay? So to find Q, we use the equilibrium expression. So that would be according to our reaction of NH3, that's our product, squared, over N2 to the first and H2 to the third power, okay, because of the coefficient of 3. So we're going to plug in these concentrations into our expression here, right? So it looks like Q is equal to 8.00 squared over our concentration of N, which is 1.50. And that, oops, you know what? I wrote the coefficient in the wrong place. That should be for nitrogen. Sorry, 3. Hydrogen is 1. Okay. Oh, wait a minute. No, I'm not reading. I keep on making this mistake. I had to write the first time, okay? That is 3, and that is 1. Okay. So we're going to leave that as 1 then. And for hydrogen, that is 1.00 to the third. Okay? And when we solve for Q, do all the math, we solve for Q, we should get Q at 43. Okay? So if we look at Q as being 43, and our Kc value is 1.7 times 10 to the second, that just tells us then that Q is less than our Kc value. So Q, let me write that a little bit better. Q is smaller than Kc. So if Q is smaller than Kc, that tells us that the reaction has not been at equilibrium, or we have not established an equilibrium. And it tells us in reality that the reaction is really proceeding to the right, and it is product favored. Okay, so our reaction is faster in the forward direction here currently than it is in the reverse. Okay? So we're making a lot more product than we are reactant at this point, and we haven't achieved equilibrium yet. Okay? So hopefully you kind of get that idea. So reaction, in other words, I'm going to write this out in your notes. Reaction proceeds to the right in favor of products. Alright, so there you go with that problem. Hopefully this makes sense, the whole idea of how to use Q here. Right, so let's do one more example problem. Here we have a reaction that's occurring. Here's the reaction. It's occurring at 448 C. The Kc value is 50.50 at that temperature, and we're gonna predict in which direction the reaction proceeds to equilibrium if we start with these particular moles in a 2-liter container. Okay, so in this case we're actually starting with moles and not molarity. So before we can do anything, we're going to have to convert everything into moles. Okay, so I'm going to go to a whiteboard here so that I have more room to do this problem. So our reaction, remember, is H2 plus I2, reversible reaction with 2HI. Okay, the equilibrium expression, writing for Q, is going to be HI squared over H2 and I2. Okay, so there's our expression for Q. Now we got to convert everything into molarity, so we're going to take 2.0 times 10 to the minus 2 moles, and we got to divide by 2 liters because that's essentially our container, and that's going to lead to 1.0 times 10 to the minus 2 molar of HI. And we're going to take our 1.0 times 10 to the minus 2 moles divided by 2 liters is equal to 5.0 times 10 to the minus 3 molarity of H2. Again, we're just converting our moles into molarity units. 2 moles divided by 2 liters, and that equals 1.5 times 10 to the minus 2 molar of HI. So these are our concentrations that we're going to use in our expression here to solve for Q, and to see if we're at equilibrium or not, or which direction we're proceeding to get to equilibrium. Okay, so I'm going to erase all of this now that I know our concentrations, and to give me room. I'm only erasing this to give me room here to solve the rest of this problem. So I'm going to plug in those concentrations into our equilibrium expression. So I'm going to take our HI, which we found was 1.0 times 10 to the minus 2, and we're going to square that over our, let's see, 5.0 times 10 to the minus 3. I'm going to multiply that by 1.5 times 10 to the minus 2, both raised to 1 powers. We solve for Q, and we find that Q should be 1.3. So we look at our Q value, and remember our Kc So Kc was equal to 50.5, okay? And this is Q. So our Q value, again, our Q is less than our Kc. So since Q is less than Kc, which direction is the reaction proceeding to? Well, it's proceeding to the right. It's product favored, okay, at this particular point in time. That means that our forward reaction is going much faster than the reverse reaction in order to get to equilibrium. All right? And that's just essentially how we use Q every time. Now, if Q, again, was equal to Kc, then the reaction at those concentrations would be at equilibrium, and those would be equilibrium concentrations. And if Q was bigger than Kc, then the reaction is actually more or less moving to the left, and it's going to be reactant favored, or in other words, the reverse reaction would be going faster than the forward reaction. Okay, so that's essentially how we use Q. All right, so take note of this. Review your notes about Q and how to use Q to compare to Kc, determine the reaction direction, and that's all there is to it for this part 2 of lesson 2 lecture video. All right.